My name's Karl Benedict. My presentation today is on RF design, and it's got a focus on how the dynamics in the physical environment can really impact your RF stability and your RF performance, and also how I approach dealing with this type of thing. Now, I want to start my presentation off with a very basic and generic statement, and that is RF as a medium is dynamic. Nothing earth-shattering or groundbreaking about that. But for me, the question that statement spawns is what makes RF and wireless design so fascinating, and that's why is it dynamic? The answer to this question for me begins with a single word, and that's movement. Where there's movement, there's change and potential for change. And we have a lot of movement in RF. I mean, start with our medium. Signal propagation is the movement of radio waves away from a transmitter. Now, when we talk about signal in wireless, we tend to refer to it in a very static format. We talk about our signal level, we talk about coverage, but that makes it easy to really lose sight of the fact that the RF signal in our medium is moving and just how fast it's moving. Okay, nearly 300 million meters per second through open air. Now that's not a gentle stream of signal flowing out of our transmitters. That's like a raging torrent of movement. And it's not just flowing through open air, it's flowing through our physical environment, which to me is just an obstacle course for our signal. And that's not a static environment either. There's a lot of dynamics, a lot of movement in the physical environment. A music teacher told me something once that really changed the way I looked at things. She said, you can never hear or experience a piece of music the same way twice, because your environment is always changing and never recreatable. This really stuck with me because it didn't apply to just music, it applies to everything. And it made me realize how dynamic everything really is. If I look back, it's kind of the basis of how I design networks and how I troubleshoot. I look for the variables. I look for things that are changing. So right now we got two sources of change, two sources of movement. And if we add more variables to that, we add more potential for change. So we'll add one more, and that's our client movement. Wireless is all about client mobility, and our clients move a lot. I mean, if you think about it, when they move through the physical environment, they change their perspective on RF, they change their signal path to the AP, and they also affect signal propagation. And they're also moving within the technology, rate shifting and changing channels when they roam. So, with all this movement and all these variables, how do I design around this? How do I design around all the dynamics here? For me, I got to look at what I can control. And I got to really analyze how I can manipulate that. So if I look at signal propagation, well, I can't change the laws of physics, so I can't do anything with that. Control client movement, probably have a better chance of changing the laws of physics. But the physical environment, that was something I can work with. So I started looking at my designs and trying to figure out how I could control or minimize the impact of change in the physical environment. And I came up with a very simple, oversimplified, matter of fact, process of doing this. Identify sources of change, determine their impact, and see, do they have enough of an impact on the RF design to really warrant me adding them into the design? And then minimize the effect of that change using design techniques. Now, if we look at identify sources of change, I started really looking at the environments that I was designing wireless in, trying to define and look at the RF characteristics of the buildings. Okay? Every building's got a unique RF characteristics to it. Okay? Even two identical buildings Floor plans are the same. Take 2 dorm buildings. And they're going to have unique RF characteristics because the items brought into those buildings or how the spaces in those buildings are being used. I realized really quickly that I could divide these characteristics into 3 groups: a static group, a temporary group, and a dynamic group. Now, the static group, this is stuff we generally look at during a design survey. And to call it static is they're not really static, they're just things that are extremely hard to change in the environment. Things like the floor plan layouts, building materials. Now, the interesting thing about this category is when change happens in this group, our customers usually realize the impact to their RF environment. So they'll make design changes to their network to compensate for it. The temporary group, this is where things get a little more interesting because these are things that can change very quickly and very easily, but they normally don't change a lot, okay? Decorations, okay, function of a room, things like that. And we've all seen this in education because think about the evolution of the chalkboard to the whiteboard, then smart boards, and now large TV monitors. If the designs for the school is not a one-for-one, this is going to have a major impact on their RF environment and may require a redesign. Okay? The temporary category, the dynamic category, this is my favorite category because this to me has the most impact to RF stability than any other group. These are objects that can change very quickly, multiple times during the day, and have an instant impact on your RF environments. I've got 3 examples up here, but there's a lot more, okay? TVs on swivel mounts and monitors. Now, I see this a lot more in recent years in hospitality and in healthcare. I was at a healthcare facility just recently. A nurse's station would report intermittent performance issues. And when this would happen, they would notice that the clients weren't connecting to the expected primary AP covering this area. What we found was there was a TV that it was on a retractable mount that was able to tilt, and if it was pulled out and tilted so that it was easier to view from the patient's bed, it would impact the signal level and cast an RF shadow. And therefore, the clients would start connecting to other APs. Okay. High traffic areas. When I design a network, I look at my traffic areas, and if my signal has to cross these areas, I try to understand what happens in these areas. Do people congregate in them? Does equipment get stored in them? Now, a friend of mine reached out to me recently with a really interesting example for this. He was working an RTLS issue, and what he found was in this healthcare facility, the large food carts, okay, that they roll through the environment multiple times during the day, delivering the trays of food to the patients and picking these trays up, they get parked in the hallways at different locations. This was impacting his RTLS accuracy. Not really something you would look for during a design survey or consider. But it was a really interesting find in troubleshooting. They were able to modify the design to compensate for it. Now, doors are my favorite because, in my opinion, doors have some of the most significant impact to RF stability than anything else because every building has them. They're made from different things, and they go from minimum attenuation all the way up to extreme attenuation for fire doors and security doors. And they're always changing position, okay? And real interesting thing about them is, depending on your signal path, they can compound each other if the signal passes through multiple doors. So we've identified a source of change. How do we determine the impact of it? Now, I do this through information that I gather from design surveys or even from troubleshooting surveys. And then I use predictive modeling for this. Now, this sometimes is easier said than done because if you look at too much information in a predictive model, you can mask the effect of dynamics in the physical environment, and you can mask their impact. Here's an example. This is a predictive design I created. This portion of the building has a firewall running through it and a fire door in the hallway. When we look at this, and we're looking at it from the coverage from all the APs, with the fire door closed versus that same area with the fire door open, you don't see a significant impact to the RF environment. But now if we focus down on a single AP, the AP that's mounted by the fire door, and I see this a lot, and I'm not a big fan of this because this creates a high signal at the fire door, which creates a high potential for change. When that door opens up, now we're propagating signal at a very high signal level down that hallway. Okay? Think about what this can cause. Definitely potential increase to CCI, which could lead to capacity issues. Could be connectivity instability in clients on the far side of the door. When that door opens, they may bounce to that AP, and when the door closes, they may bounce back to a different AP. And definitely roaming. If you think about it, if you're roaming out of that area, you connect to that AP, and as you pass through that fire door and down that hall, your signal level is so high that you may not reach your roaming threshold before the doors close behind you. And if the doors close behind you, well then your signal's going to drop suddenly, and will you roam? Or will you do a hard disconnect and then a reconnect? And how's that going to impact your client? So we've identified a source. We've determined it does have an impact. How do we minimize this? I do this through micro adjustments to my mounting locations. Now in this example, when I look at this, I see two problems. The first problem I see is that there's direct line of sight through the fire door. The second problem I see is that there is high signal level at the source of change, which is the doors. Okay? By simply moving that AP back and to the right, we're using the building for isolation. We've lowered the signal level at the doors, and we've removed line of sight. We haven't dramatically impacted the coverage area. We're still within our requirements. And now if you look at that, we've definitely reduced the potential for CCI. We've definitely improved our stability when that door transitions. And now if you roam out of that area, you're going to reach your roaming threshold before those doors close behind you. So we've improved roaming. Okay? Now, a lot of people will say to me, well, that's a fire door. Okay? That's a big, heavy door and a lot of attenuation. That's going to have an impact. Regular doors won't do that. This is a predictive design I did in Hamina, and I based this on real-world data, just like the last one. And this shows an in-room AP design in a section of a building. Now, this repeats multiple times in this section of the building. Now, what I do with this is I'll draw in doors, and then I'll move the doors within the predictive design, and I'll use the undo and redo button to animate those doors to see what the impact are. So I've got a video, and in this video, we are going to focus on the room that's going to be highlighted in red. Its primary AP is being covered by the AP above it. Okay, the AP below it is blocked by a firewall. Now, the AP across the hall, with the doors in their most blocking position, and that doesn't mean closed, because two doors are closed and then the bathroom door is open. Okay? The signal's not propagating into that room. But when I start to hit the undo button, open the first room door, open the second room door, and then close that bathroom door, you'll see that we have a signal level propagating into that room at a negative 55. That's equal to the signal from the primary AP. Is that going to cause a problem? Potentially. Depends on the client, depends on what they're doing, depends on what else is happening in the environment. But what I can tell you is that you've increased your potential for an issue. And with this happening multiple times throughout this floor plan and these doors transitioning, you've now created a very unstable environment. It's kind of like, I compare it to like a road with a lot of potholes in it. A smooth road versus a pothole road, you're not going to affect the performance of the car, but you are going to increase your potential for a problem or an accident. Now, in this situation, how do we minimize this effect? I would do the same thing. I would do micro adjustments to the mounting locations and remove line of sight through the doors. By moving the APs from the center of the rooms up into the corner, we're not impacting coverage. Coverage is still adequate. And you'll see that when these doors transition, you're going to see the impact to the RF environment has been minimized. And we've increased RF stability. This, to me, is something that we can't eliminate it. We can increase RF stability, and we can preserve our RF environment for performance, okay? I'm going to play the rest of this video, and it just shows how I move the doors around and I use the undo and the redo button to animate this. But it can be done with anything. Attenuation areas made to simulate people, doors, any kind of movement in the physical environment. So I'm going to leave you with the final thought, and that is, as requirements get stricter, as we start to use higher frequencies, because higher frequencies are going to be more impacted by movement in the physical environment, RF stability, in my opinion, is going to become as important as things like coverage, capacity, and good roaming environment. If we can increase RF stability, we're going to preserve our RF environment to better support the performance we're designing into our networks. So, thank you very much. I appreciate your time and look forward to talking with you.